Dear students, in this class we will have a review on Bohr's theory of atomic hydrogen. I know that you have some idea on Bohr's postulates, and I will not discuss a lot about that. In the presentation I made in the slides, I shared it with you. You have seen that how was Bohr's theory developed, and the postulates and the merits and demerits of Bohr's theory were highlighted there. So I will not discuss everything about Bohr's theory, but some discussions and some interesting features of Bohr's theory will be made here in this class. And what we learn from Bohr's theory is that there are stationary circular orbits for electrons. Electrons circulate around those orbits. Not any orbit, some particular orbits are allowed where the electrons will not radiate energy, and those orbits are known as stationary orbits, as you know it. These are stationary orbits, and Bohr quantized the angular momentum. Electrons will move around some particular orbits in which the angular momentum of electron, which is mvr, will be an integral multiple of h by 2 pi. That means n into h by 2 pi, where n is an integer. This is a very important relation, and the main contribution of Bohr lies in this part, that as Planck quantized the amount of emitted energy or absorbed energy, and in case of photoelectric effect, as Einstein quantized the radiation, that means light, by introducing the concepts of photon. In Bohr's theory, Bohr quantized the angular momentum of an electron in atomic hydrogen. And what we learn more is that emission, absorption of energy during a transition of electron will take place when an electron jumps from one orbit, say mth orbit, to nth orbit. This sign is the difference sign, em minus en, or the other way, en minus em. This is the difference sign. Then energy will be emitted, h nu. We know it, it will be emission if em is greater than en, and it is absorption if em is less than en. Now, we all know this, and we use the force, and I think it will be mvn square by r, not rn square. This is wrong here. Please make a correction. There is no square. mv square by r is z square by 4 pi epsilon 0 rn square. You all know that. And from the quantization relation using these things, we find that Rn is the radius of nth orbit, is this expression, and the energy of the electron in the nth orbit is this relation. I tell you to be careful about these expressions. Don't trust what is written here. Just check it, do the calculations on your own, and check it with any you will find it any standard book. Check it with the books, and also check whether these expressions are written correctly. Just take the idea from what I say and do the calculations on your own. And if the mass of the nucleus, as we see it here, the mass of the electron is taken as m here. This m is the mass of electron, and it is considered in Bohr's theory that nucleus is infinitely heavy. Though nucleus has a finite mass, in case of atomic hydrogen it is a proton actually, and when the mass of the nucleus is considered to be finite, then from you know how the central force cases, actually in two body problems, how the concept of reduced mass arises. And if you consider the mass of the nucleus is finite, then the mass of electron is replaced by mu, where mu is known as the reduced mass and is given by this relation, where everything is written here. Capital M is the mass of the nucleus, and so on. In case of infinitely heavy nucleus, we place capital M equal to infinity, so 1 by mu equal to 1 by m in that case, and your reduced mass is the mass of the electron what was used here. In case of infinitely heavy nucleus, this is the relation, and if you want to use finite mass of the nucleus, you replace this m by mu. As simple as that. And the frequency of the emitted radiation is like this. This is a higher orbit, EM, and the nth orbit we say is the lower orbit here. This is the nth orbit. So higher orbit to lower orbit, one electron jumps. It initially was here, so it is drawn as a dashed line, and it jumps down to the lower level, and one photon is released as you see here. And this energy E equals h nu. If we write it in terms of wave number, where nu bar is the wave number, which is the reciprocal of the wavelength, then nu bar follows this relation. Z is the atomic number, it is 1 in case of hydrogen, and R is known as the Rydberg constant. R is the expression for R is given here. And follow any textbook, you will find a discussion on Rydberg constants. In fact, as I discussed it in the slides, all these formula were actually derived before the theory of Bohr actually. So this is actually matching with the Rydberg formula for spectral lines. And the energy of a state, as we see it from here, the energy of a state of an electron, what does it mean? In an orbit in atomic hydrogen, an electron is bound. As you see it, its energy is negative. What does this negative energy means? It means you need to supply energy from outside to take the electron out of the atom. That means you want to free the electron from the field of the nucleus. So you have to put energy within the atomic system, so that electron's energy becomes more and more positive, and ultimately it becomes zero. So electron is out of the atom, that means the electron is free when this En is equal to 0. And from the expression we see here, En becomes 0 if N becomes infinity. So when theoretically N becomes infinity, only then the electron is free. Otherwise, however large is the value of N, the electron is bound to the atom, and for large n, the energy will be very close to 0. And if n is small, then the electron is bound very tightly to the nucleus. This is seen from the expression. So the energy of a state may be determined from the amount of energy needed to give to the electron to make it free from that state. So if we say it is a transition, then it will be, the electron will be here in the lower state and will go up by absorbing energy to the higher state, and in the higher state the energy is 0. Then the electron is said to be free, and the amount of energy needed is definitely the amount of energy of this state. Then the energy of the final state is 0, so energy of the nth state is in terms of this expression will be that means in terms of the Rydberg constant, this comes out to be of this expression. Simply here we see, compare it with the equation number 2 or expression number 2, and if we can write it in this way. The energy of nth state in terms of the Rydberg constant. And from Bohr's law we can calculate the Bohr series. You know that the Bohr series lies in the visible range. So Bohr series was experimentally discovered first, then other series like Lyman series, Paschen series, Brackett series, Font series, all of them are introduced and were discussed in the slides I have given you before. And the Bohr series, as for example, we see that for atomic hydrogen, if you put Z equals 1, N equals 2, that means the final state with quantum number 2, and the initial state, that means the M values are 3, 4, 5, etc. higher. See the diagram here again, N equals 2 and M is higher than 2 for the Bohr series. So you obtain the Bohr series here. This is the Bohr series. where you see 1 by 2 square, that means the final state, and 1 by m square, m is the higher states and r is the Rydberg constant, z equals 1. Similarly, other series are found. You can do it easily by your own. And the ridge combination principle is the next topic. What is ridge combination principle? It said that if there are different energy levels, in fact, we discuss the ridge combination principle from Bohr's theory. Say there are 4 states, 1, 2, 3, 4. Let this one be the ground state, 2 is the first excited state, this one is the second excited state, and this one is the third excited state, and so on. So an electron can jump directly from 4 to 1. And in that case, the amount of energy emitted is given by, I have written it that the emission line is given by, and the same thing here, that nu 41 is the frequency, E4 minus E1, that is not correct. In fact, there is a mistake. This is h nu. The emission line, this is h nu. Okay, this is h nu, is E4 minus E1. Now, it is possible that the electron can come down via 3 possible emission of photons in a step-by-step manner. First, it comes from 4 to 3, releasing 1 photon, then 3 to 2, releasing another photon, and then 2 to 1, releasing another photon. And you can write it in this way, E4 minus E1, as a difference between 3 gaps between 4 levels. You can write it. So, from E4 minus E1 is this one. So, you write the relation between the frequencies. If it is it comes down, the transition takes place directly from 4 to 1, or it takes place via some intermediate steps. Now note that in most of the books you will find 3 levels, 1, 2, 3, and it will be given like E31 equals E32 plus E21 in this way. But actually take a note of it that transition between any 2 levels, any 2 states, transition is not possible. And there are certain things on which it is decided, like the parity of the states, like the angular momentum of the states. You will learn it later, that some transitions are allowed and some transitions are restricted. And that means to have a transition, you need to have some selection rule. This selection rule will choose the allowed transitions. Some rule has to be satisfied, which transitions or transition between which levels are allowed. And it can be seen that though in many books it is given by 3 levels, but actually such a transition is not allowed due to selection rules. Say if an electron comes from 3 to 2, it is allowed, and if it comes from 2 to 1, it can also be allowed. But in that case, no photon is possible which will be emitted due to a transition from 3 to 1. So to have an allowed transition, you must have 3 step-by-step transitions. So I have given it involving 4 states, which gives rise to 3 transitions. You can understand it later, but just take a note of it. And if you have queries, please write to me. Now we discuss a very important topic, the last of this series, in fact today's lecture, that is the Bohr's correspondence principle. What does it say? It says correspondence means some relationship between between 2 things or 2 views, some correspondence. And actually Bohr's correspondence principle is a kind of bridging between the Bohr's quantum theory, which is kind of ad hoc theory. There is actually no theoretical background, no foundation of physics which leads to such a theory. As why is angular momentum quantized? As why do electrons revolve around some particular orbits, and they will not emit any energy. No explanation of these are given, but if you assume these things, then the result is very much satisfactory. So this theory cannot take us, Bohr's theory cannot take us any background, but it is ad hoc in nature, and also is Planck's theory, it is also ad hoc in nature. However, Bohr's theory do not tell us anything about the intensity of spectral lines. Though it predicts the position of the spectral lines, the spectral line positions, I have not written the term positions, but it is almost understood. The spectral lines were explained, but not their nature, kind of what is the intensity of them, what is the state of polarization of them. From Bohr's theory, you cannot calculate those things. But it is known that classical theory, using classical theory, these issues like the intensity of spectral lines, polarization of spectral lines, those can be calculated by using classical theory. But Bohr's quantum theory cannot say anything on that. So there is a difference. In some cases, classical theory gives us some advantages which is not yet available in Bohr's theory. Another point, very important, that as we see En, energy of nth orbit, is proportional to n square, so that electron is free when n equal to infinity, and for a very high n, which is finite, the energy levels are very closely spaced. So it is a very important thing that the energy levels are very closely spaced for a very high n. So n being sufficiently high, there is an energy level which is close to 0, and say you take now n, increase the quantum number by 1. So previously it was n, which is very close to 0, and now it is n plus 1, which is also very close to 0, in fact more close to 0. So the difference between nth energy level and n plus 1th energy level is very, very, very narrow. It is therefore can be said that very for high n values, the energy levels are almost continuously distributed. So if the energy levels are continuous, in that case the classical theory can be applicable. This has a very important consequences, and we will see whether the classical theory is really applicable for very high values of n. So it was thought that in such conditions that there are some failures in this, mainly in this case, that Bohr's theory cannot say us about the polarization or intensity of the spectral line, and it is now at that point of time it was thought that a bridging between classical theory and the new quantum theory of Bohr should be attempted. And according to classical theory, as you see that it's a very common, the frequency of the spectral line should be equal to the orbital frequency of the electron, because according to classical theory, when radiation is emitted, it is according to the frequency of oscillation, as we have seen it also in Planck's theory. The frequency of oscillation must be equal to the orbital frequency of electron. Let that frequency be termed as Fn. We name it as Fn, frequency of the electron, orbital frequency of electron in nth orbit. So Fn equal to omega n by 2 pi, omega n is the angular velocity equals Vn by a. Vn is the velocity of electron in the nth orbit, Rn is the radius of nth orbit, and so on. It's simple higher secondary or maybe very basic knowledge of physics. And now according to Bohr's theory, we know that En, energy of nth orbit, takes this value considering z equal to 1. Remember, we are dealing with hydrogen. So otherwise there would have been a z square. Now for transition between two levels where n is sufficiently high, very high, and for both the levels are sufficiently large, then delta En comes out to be using this En, and as you did in case of difference calculations or in case of error calculations, you did it that delta En takes this value. The term n square here gives the rise to the term 2 delta n by n cube. This here with a negative sign, for which this negative sign is absorbed. You have had one negative sign here, so this is absorbed in the calculation of delta En, which gives you h nu. Delta En equals h nu. We knew it. E2 minus E1 equal to h nu and so on. From our knowledge from Bohr's theory, that nu equals this one. You see that one h comes in the denominator in the right hand side. Here it is h square. Here it is h square, and in the next expression in the right hand side is h cube. And again, from quantization of angular momentum, we knew from Bohr's theory that mvr equals nh by 2 pi and m omega r square. As you just carry on the calculation, from here you calculate the value of nh and put nh cube here in this equation. From this expression, you go back, from this expression, you go back to this expression. Put the value of nh and you get the expression of nu as given in equation or expression 4. And from the equilibrium condition of the orbit, we know that mr omega square equals the centrifugal force, that is equal to the Coulomb attraction, from where actually the energy of electron is determined. We write this application to calculate this 1 by r square value, and this 1 by r square value, or 1 by r square and one another r is here, so it is 1 by r cube. This 1 by r cube is now fed back again and fed back here in the expression of 4. This is r to the power 6, and here you use r cube, and using all these things you calculate. You see that nu becomes omega by 2 pi into delta n. Do all the calculations. It will be some omega n. I have missed the suffix, and here it will be Rn. So make the calculations, corrections, I'm sorry. So our nu is omega by 2 pi into delta n. Now if you say that delta n equals 1, that means transition is taking place between two consecutive levels. Then our omega n equals Fn. What is Fn? Fn is actually, as we have seen, omega n by 2 pi means the frequency of the orbital electron in the orbit, the frequency of circulation in the orbit, which is the classical result. That means your frequency of I am sorry, I have made another mistake in the symbol here. It is nu equals Fn. Nu equals omega n by 2 pi. So it is nu from equation 6. So nu equals Fn. And that means this nu is the frequency of emitted light. This nu is the frequency of emitted light, and this Fn is the frequency of oscillation of the, or a frequency of circulation of the electron in the nth orbit. So these two become same, as we have tried to propose before the start of the discussion. According to classical theory, the frequency of spectral line should be equal to the orbital frequency of electron, and from calculation of Bohr's theory we find out that it is happening. Therefore, emitted of the frequency of the emitted energy for transition between two levels of very high quantum theory as calculated by Bohr's theory is same. The frequency of emitted energy is same as the classical orbital frequency Fn. And if you use delta n equal to 2, you will obtain nu equals 2Fn. That means the higher harmonics. If delta n equal to 2, 3, 4, the higher harmonics are generated, which is allowed in the classical theory. From Bohr's theory, we find that. And therefore, we see that Bohr's correspondence principle says that behavior of an atom as predicted by the quantum theory, as it says, corresponds to the results of the classical theory when the quantum number is large. When the quantum number is large, Bohr's correspondence principle says that the results of quantum theory and the results of classical theory, they become identical. Another point here, we see that here the harmonics are generated and you see no result is possible with fractional values of delta n, which actually is kind of a linking between Planck's law and Bohr's law. That also comes from this correspondence principle that Planck told that the emitted energy is quantized. In this case also we see that emitted energy is either nu, or as the frequency is Fn, and it will be nu for delta n equal to 1, and if delta n equal to 2, it will be 2 nu and 3 nu. So and the frequency of oscillation and the frequency of the emitted energy, that is also quantized. No intermediate value is allowed here. We can also get a glimpse of the Planck's law from the Bohr's correspondence principle. And we are going to close our discussion today, and before we end, we just say that this correspondence principle was used by Bohr and also by other workers at that point of time to estimate the line intensity, to estimate the state of polarization of the emitted photon, and also to formulate the selection rules for which transition are going to take place and which are restricted. So by this we end the discussion on Bohr's theory, and then in next classes we will do some problems, and then we will proceed to other corrections on Bohr's theory made by Sommerfeld. Okay, we end here today.